Hello everyone, my name is Selina. I am Assistant Professor of SBIST Department of Mathematics. Today I am going to discuss a problem on sequence. Proof that the sequence root over 3 plus root 3, root over 3 plus root over 3 plus root 3 and it's an infinite sequence is convergent, and also find its limit. So first we write this sequence as a sequence xn, where x1 is root 3, x2 is the second term root over 3 plus root 3, x3 is the third term, and so on. Again we can write x2 in terms of x1 as x2 is root over 3 plus x1. That means this root over 3 can be replaced by x1. Similarly, we can write x3 in terms of x2 as root over 3 plus x2. And if we write in such a manner, we can get a recurrence relation xn equal to root over 3 plus xn minus 1, and similarly xn plus 1, which is the n plus 1th term of the sequence, is root over 3 plus xn. So to handle this sequence, first we have to remove the square root, and for this we have squared both sides and get xn plus 1 square equal to 3 plus xn. Now students, to prove a sequence convergent, what we have to do? We have to use two theorems. One theorem is if a sequence is monotonically increasing and bounded above, then we can say that the sequence is convergent. And the second theorem is if the sequence is monotonically decreasing and bounded below, then we can also say that the sequence is convergent. So first we have to check whether the sequence is monotonically increasing or decreasing. So to check this, we have write xn plus 1 square is equal to 3 plus xn and xn square in terms of xn minus 1. Now we can subtract these two equations and get a relation xn plus 1 square minus xn is equal to this xn minus 1. Now we all know the formula of a square minus b square, so we have baked this in the formula of a square minus b square, and we get the relation 3. Xn plus 1 plus xn into xn plus 1 minus xn is equal to this. Now see, every terms of the sequence of which we have written in before, that x2 is root over 3 plus x1, x3 is root over 3 plus x2, and x1 is root over 3. That means every term of the sequence is positive. That means we can write xn greater than 0 for all n belongs to n. So in this relation equation 3, the first part is positive. Now the second part can be positive or negative. If the second part is positive, then the whole product, which is equal to the right hand side of equation 3, must be positive. And if this part is negative, the second part of equation 3, then the right hand side will be negative. Now we have to check what is going on. See, from the given relation of the sequence, every term of the sequence can be written as x2 is root over 3 plus x1. That means x2 must be greater than x1, so we can write x2 greater than x1. Again, if we see x3 is root over 3 plus x2, so x3 must be greater than x2. And if we go with this manner, we can write the n plus 1th term of the sequence, that is xn plus 1, is greater than its nth term xn. We can get the relation 4. Now in monotonically increasing sequence, what we have to check? A sequence is monotonically increasing if a sequence xn is said to be monotonically increasing if the n plus 1th term of the sequence is either greater or equal to its nth term for all n belongs to capital N. That means the set of natural numbers. If this condition holds, we can say that the sequence is monotonically increasing. Now, in our problem, what we get? We get that x n plus 1 greater than xn. So, in equation 3, this term is also positive, this term is also positive. That means the difference xn minus xn minus 1 is positive. So, from 3 we can get the relation xn minus xn minus 1 greater than 0. That means we can also write xn greater than xn minus 1. This condition actually satisfies that the sequence is monotonically increasing. From this relation we can write xn is a monotonically increasing sequence. Okay. So to check the sequence is convergent, first we have proved that the sequence is monotonically increasing. Now students, we have to see whether the sequence is bounded above or not. If this is bounded above, if the bounded above condition satisfied, then we can say that the sequence is convergent. So how can we prove that the sequence is bounded above or not? Now from the relation 4, we can write xn plus 1 greater than xn. And if this condition holds, its square terms are also greater. Now, from first we have get xn plus 1 square is equal to n plus 1 equal to root over 3 plus xn. So if we squared both sides, we get xn plus 1 squared is equal to 3 plus xn. We have substituted this value here and the xn square remains as it is. Now all the terms are taken in the same side and we get the relation xn square minus xn minus 3 less than 0. Okay, we get this relation. See, this is a quadratic relation and now we have to factorize this. So how can we factorize this quadratic equation? If this less than 0 does not hold, if it is equal to 0, then this will be a quadratic equation. So we can factorize this by two ways, either middle term or using Sridharacharya's rule. If middle term cannot be done, then we use the Sridharacharya's rule. See here, we have write it as equal to 0 for our ease of the calculation. Using Sridharacharya's rule, we can find xn as this. That means this quadratic equation can be written as the product of these two factors, 1 plus root over 13 by 2 and 1 minus root over 13 by 2. So here in equation 5 we have done that part. Okay. Now the second part. See the second part. Now see the second part. 1 minus root over 13 by 2. This quantity is negative. Why? Because root over 13, root over 9, we all know root over 9 is 3, root over 16 is 4. That means root over 13 must lies between 3 and 4. And therefore 1 minus root over 13 is a negative quantity. And therefore 1 minus root over 13 by 2 is also a negative quantity. Now, if xn is subtracted from a negative quantity, then this part is actually positive because 1 minus root over 13 by 2 is itself a negative quantity. So minus a we can get plus. So this part is actually positive. Now to satisfy the condition 5, the first part, that is xn minus 1 plus root over 13 by 2, it must satisfy this condition that it is less than 0. That means we can write xn less than 1 plus root over 13 by 2. Okay. Again, if we see the given equation, we can see x1 is root over 3, which is a positive term. And as x1 is positive, all the terms of the sequence are positive. That is xn greater than 0 for all n belongs to n. So combining these two conditions, we can write xn lies between 0 and 1 plus root over 13 by 2. From these, we can write that the sequence is a bounded sequence. Now first we have proved that the sequence is monotonically increasing, and now we have proved that the sequence is a bounded sequence. Bounded sequence. And hence we can write xn is a convergent sequence because both two conditions are satisfied. Okay? So for the first part of the problem is solved. Xn is a convergent sequence which we have proved. Now we have to find the limit of the sequence. How will we find the limit of the sequence? Now suppose the limit of the sequence is L. We have a relation in hand xn plus 1 square is equal to 3 plus xn. If we apply limit on the both sides, we get this limit n tends to infinity xn plus 1 square is equal to 3 plus limit n tends to infinity xn. Now this is L square and this is 3 and this is L. So this is a quadratic equation. Now as usual, solve this by Sridharacharya's rule and you get two values of L, 1 plus minus root over 13 by 2. But 1 minus root over 13 by 2 is a negative quantity, so we discard this and hence L will be 1 plus root over 13 by 2. Why we discard this? Because the sequence is a sequence of positive terms. Since the sequence is the collection of positive terms, therefore its limit must be positive. So we discard the negative part. Therefore L will be the positive quantity 1 plus root over 13 by 2. And from this we can write the limit of the sequence xn is 1 plus root over 13 by 2.